center. So the current is like this.
This ring is circular, right? It's just oval
Yeah.
to make
It
it
looks
look.
like an ellipse, but you know, it's
It's just to give it the angle.
yeah. Okay, so we start with B sub r law. dB equals all of these constants. And then we have dl cross r hat over r squared. So let's draw a dl somewhere in the ring. How about we draw it at the top? Now, which way is dl pointing at the top of the ring given the direction of this current? So mind you, what we have is this. The axis from your perspective is horizontal, and this is the ring. And the current is this way. At the highest point here, what is the direction of dl, the vector dl?
Towards us.
Yeah, towards you. The L is along the wire in the direction of the current. If the current were the other way, the L would be towards me, but it is towards you. So at the top, the L is out of the board. Yes? So, but you know, how do I draw a vector that sticks out of the board? So I'm going to try to draw it like this. I mean, it doesn't look like it's out of the board. It looks like it's at an angle, but it's supposed to be coming out of the board. Yes? Now, that's the L. What is r hat? R hat is defined as, well, what is R? R is the distance from the L to where we're calculating the magnetic field. So R, we're calculating the magnetic field there. So R is this. And R hat is a unit vector along R, starting at, you know, from the L to the field point. So R hat is this. Now, again, it looks weird over there. So let's go back to this picture. Because this, I think, helps. So this is the axis, this is the ring. I want to know the magnetic field here, let's say. The current is this way. I gave it that direction. I could have given it the other direction, but I just gave it that direction, right? So at the highest point, the L is towards you. Now, R hat is from the L to the field point. It will be this way. Right? What can you tell about the angle between the L and R hat? It's 90 degrees. Essentially, or maybe I'll use this picture, the L is this way, out of the board, and R hat is like that. And the angle between those two is 90 degrees. Right? So when I calculate this at the top of it here, you know, what is the L cross R hat? The L cross R hat, well, what will be the magnitude of that? It will be the magnitude of the L times the magnitude of R hat times the sine of, in this case, 90 degrees. And what is the magnitude of this unit vector? 1. The sine of 90 degrees is 1. And the magnitude of that, I'm just going to call it the L without the arrow above it. So the L cross R hat is just the L. Now, what is the direction of the L cross R hat? Maybe it's better that if I put it over here. The L is out of the board, R hat is this way. What has to be the direction of the L cross R hat? It's going to be perpendicular to both of them, right? So there are only two possibilities. This way or this way. So which is it?
Up the page.
So the magnetic field at this point is going to be this way. so that this is 90 degrees. Right? It has to make sense. You have to be able to see it. It's got to be perpendicular to both of them, right? So that's going to be the direction of that magnetic field, right? Now, what if I choose the L down here at the bottom? So in this case, the L is into the page or into the board, right? The L is into, right at the bottom of this. So in the picture here, the current is like this. So at the bottom, the L is into the board, but the field point is up here. So now you have this is into the board and R is this way, so R hat is that way. From the L to the field point. So what is the direction of the cross product of the L and R hat? It's gotta be perpendicular to both of them. So it'll either be this way or that way. The L into, or maybe put it like this. Into, it will be?
Down to the right.
Exactly. It will be this way. And, the only difference between these two, besides the direction, right? It's just a direction. And if I consider the other DLs, what I'm going to find out is that the magnetic field sweeps a cone around the axis. So the magnetic field, like if I consider the ring at the top, the magnetic field is like this. If I consider the magnetic field from the current at the bottom, it's going to be like this. And if I go all the way around, the magnetic field is going to be like this. Always making the same angle with the x-axis. So what I'm going to do is this. I'm going to say, well, from symmetry over here, what will happen to the y components of these magnetic fields when I add them up? They'll cancel out. So I'm just going to calculate the magnetic field of the x component. The x component of the magnetic field. So I'm going to call this angle theta, but that means that this angle here is theta. This is A, right? Because this is complementary to that one, but this angle is complementary to that one because this is 90 degrees. So what I'm going to do is this. I will say that what I want is the x component of this dB. So the x component of that is this. So dB sub x is the x component of dB, which is going to be dB cosine theta, right? And so this is the magnitude of dB. So what is the magnitude of this? It's just mu naught I over 4 pi, the magnitude of the L cross R hat over R squared, right? But the magnitude of the L cross R hat is this, right? Just the L. So this will be, well, I'll write it over here. This will be mu naught I dl over 4 pi r squared, and this is just dB. I'll write it without the absolute value sign because I'm removing the arrow above the letter. That's the magnitude of dB, the magnetic field generated by the current in that little segment, dl. So I take this, I plug it in here, and I get mu naught I over 4 pi, and then I have an r squared, and then I have a cosine, I have a dl and a cosine of theta, right? And this is the x component of the magnetic field dB. And when I do the sum over all the other DLs in the ring, all of those x components are going to be pointing in the same direction. So the total value will be the sum of them. And the sum of that, I'll just write it out like this, and then ask you a series of questions. Okay, this integral on the left-hand side is just going to be the x component of the net magnetic field, right? Which, we can just say also that, the net magnetic field, the total, is in the x direction. And then, I have this integral here. Now, mu naught is a constant. I is a constant. 4 is a constant. Pi is a constant. Now, you tell me, is R a constant? If I go from every point on this ring to the axis here, is that R the same for all points?
Yep.
Yes, so, oh, nice. I can put it outside the interval. What about the angle theta? The angle that R makes with the radius. Is it the same if I go to all points?
Mm-hmm.
Yeah, okay, good. I can put it outside. And then I just have the integral of the L, which is, I know you want to say, oh, the integral of the L is L, because that's what you've been trained to do, right, in math. But it just means the sum of all the DLs, right, which is the circumference of the ring, 2 pi a. So the total magnetic field is, this is that, right? But then I can just now write, okay, the magnetic field is to the right, and as a vector, well, maybe I'll just write it up here. Magnetic field net is to the right. I'll use the I hat. And then I have mu naught I. Okay, so what is the cosine of theta? Can we do something with this cosine of theta? What's the cosine of theta? It would be A divided by R, right? But what is R? The square root of x squared plus a squared, right? So this would be A divided by the square root of x squared plus a squared, correct? Notice that I also have an R squared over there, right? What is R squared? It's just x squared plus a squared, right? So I'm going to put those in. So the magnetic field is I hat mu naught I instead of cosine theta. I'm going to write A over x squared plus a squared to the 1/2. I have a 4 pi downstairs. And instead of R squared, I'm going to write x squared plus a squared, right? And the L is 2 pi a. So this pi cancels that pi. This 2 is going to cancel one of those 2's over there. And I get for the answer to the right. And then I have mu naught I. And then I have a squared, the radius squared. And then downstairs I have a 2 from over here. And I have x squared plus a squared to the 3/2. Now, I haven't checked. Did I make a mistake? Well, let's do something. If I evaluate this magnetic field at x equals 0, which is at the center, what was the answer that we got before? If you look in your notes, it must have been mu naught I over 2a, right? So, if x equals 0, then b will be I hat mu naught I a squared over 2, x will be 0. Now, what is a squared raised to the 3/2? A cubed. So therefore, I get mu naught I over 2 A. So I'm good. I'm confident that I didn't make a mistake. This is probably the next easiest problem because when you set up this integral, everything is a constant. And you end up just summing all the DLs. It's a more interesting problem if some of these quantities are not constants, and then you have to figure out a relationship between the different variables before you can do the integral. And of course, what's a little difficult about this problem is being able to see this in 3 dimensions, right? You have an axis like this, and you have a ring like that, and you gotta consider, if this is the L, r hat is from there to the field point. But then you'll see that they are at 90 degrees to one another, so that facilitates calculating the cross product. The L cross r hat is just gonna be the magnitude of the L times the magnitude of r hat, which is 1 times the sine of 90. So all of that is just gonna have a magnitude of the L. But the cross product is gonna be perpendicular to that. But then you consider other points just to check, and you'll see that the magnetic field points in a different direction. And then you say, oh, is there a component that will cancel out? And so that I can just calculate the other component. And you get that in this case, the component that will survive is the one along the x-axis. So you write dB cosine theta is dB sub x, and then this is what you sum. So you have this, that. And then it turns out that over here, the integral boils down to this, which is just the sum of the length around the ring, which is the circumference, 2 pi a. What I'll do next time is I'm going to consider this. What happens if you have a wire of finite length, like we did for the case of electric fields, to L. And I'm going to go above the midpoint. So this is L and this is L. And suppose there's a current to the right in this wire, just that segment of the wire. And I want to know what is the magnetic field there at a distance, let's say Z, which is fixed above the midpoint. What's the magnetic field there? And in this case, I'll do this problem next time. You just say, well, I choose a DL this way. I can just call this the x-axis, so therefore I can call just this dx instead of dl. And r hat is going to have to be this way. And what's interesting in this case is that when you do the cross product between r hat and the L, they're both on the same plane. The angle between them is not 90 degrees between the L and r hat. And if I choose the L over here, then r hat is 90 degrees to the L. But if I choose the L over here, r hat is like that. The angle is not 90 degrees. So the angle is going to be a variable. The other thing that's going to be a variable is the distance r. If the L is over here, the distance is this, z. But if it's over here, the distance is this. So r is going to be a variable. So the only difference really is that this is not going to be a variable anymore if there's a theta in there, and this is not going to be a variable. And then we'll just have to find out a relationship between them to do the integral. Okay, but the rest is, okay, don't fall behind. So, are we doing a quiz next? Oh no, you just took one, right?
Yeah.
It's like, what are we doing a quiz?
So, the week after next, we should be thinking about a test. Like the Wednesday after that? Like, how about 2 weeks from today? That'll give us